Hello, everyone, and thank you for joining us for today's session. My name is Askia, and I am the Facilities Coordinator for the Redmond Reactor Space. Before we get started, I've got a few things to go over, so please take a moment to read our Code of Conduct, which we've posted in the chat. Let's go ahead and take a look at that. Basically, we seek to provide a respectful environment for both our audience and presenters. We encourage engagement in the chat, but please be mindful of your commentary, remain professional and on topic. We're going to share useful links throughout the chat, and this session will be recorded and will be available on demand within 24 to 48 hours, and that'll be on the Microsoft Reactor YouTube channel. That brings us to today's session. This is going to run approximately for 1 hour, and there'll be time for questions throughout the session. So now I will turn it over to our speaker, and we will get started.
Hello, everyone. Welcome to talk. My name is Yang Song. I'm a principal software engineer at Microsoft on the Industry Solutions Engineering team. We work with client engineers on code with projects to create innovative solutions using Azure service and technologies. So before I start, I'd like to remind you to fill in the 2-question survey I posted in the chat window. That'll give me some idea as to how familiar you are with the topics that we are going to talk. And I'd also like to give you a little background of myself. I was born and raised in China and got my bachelor's degree in computer information science back home before coming here for my master's. I've been in the software development field for the past 25 years and have worked on systems of all sizes and architecture types. My focus is to architect and implement efficient systems that are easy to maintain and expand. The goal of today's talk is to introduce the concept of the control plane for software systems, and also to present you some experimental solutions that you could refer to kickstart your own development of the control plane. So today's agenda, we'll first talk about the problem statement. What is a deployment stamp? What is a control plane? And what are the control plane functionalities? What are the actual services that we could use to help us to implement the control plane? It'll be followed by a quick demo and a Q&A session. Of course, if you have any question as I talk, please feel free to put into the chat window, and I'll review from time to time and answer as appropriate, okay? So now, the problem statement. It's hard to manage horizontally scaled stamped applications. And before I dive into figure out why, let's take a look at the if any survey results came in. Oh, perfect. So it looks like we have a mixed crowd today, and some of you, the concepts may be new, some are more familiar. So I'll spend some time to explain the terms so that we are all on the same page. A deployment stamp, in my opinion, is infrastructure as code script that provisions the infrastructure, the services, and the applications that serves the complete system functionality, but only a fraction of the user base. Multiple deployments of the stamp in the same region or multiple regions would work together to shoulder the load and serve the complete user base. Each deployment of such stamp is called, sometimes it's referred to as a scale unit or a stamp. So what are the use cases for a stamped architecture pattern? There are many reasons that we want to use that. For example, all the services or some services have inherent resource limits. So there may be the limit on the number of incoming connections that can be created or TCP sockets that can be present. And then the scaling of the service may not be linear. As the service getting closer to the scale limit, the performance may decrease badly or the cost may increase prohibitively. And then there's also geopolitical or geographical reasons. For example, some country requires that any software system or data has to run within the territory or within the continent. And a very common use case for the stamped architecture is for high availability systems that has very stringent SLA, the 394959s. When individual scale unit may present a higher downtime, when multiple scale units run together and fail over for each other independently, it's going to greatly reduce the downtime. Of course, there's also RTO and RPO considerations. Recovering from a system that supports 100,000 users theoretically would run a lot faster and easier than supporting a system that supported 1 million users. So in our particular use case, our client has to support hundreds of millions of users worldwide. So all of the above use cases would come into play. And depending on the scaling needs, at any given point of time, there could be tens, hundreds, or even thousands of scaling units running at different regions. So now you get a mental picture, like all these systems spawning off like everywhere. So how do you manage them? How do you know which scale unit is coming up or going away or is having problems or is working properly? So that's where the control plane can help. And control plane is not a new concept. In Azure, we have the concept of control plane and data plane, where the control plane would handle the provision and management of the resources, and the data plane would handle the functionality of the services. So it's the same concept here. The control plane for the software systems would first of all, define the configuration for the scale unit. Right? What are the services and resources and applications that's necessary to support our system functionality? How do we allocate these resources? What are the dependency requirements? How do we deploy software? What is the deployment strategy? What is the rollback strategy? What if we need to upgrade a service? How do we do all these maintenance without the user being impacted? And how do we decide if we want to scale up or down versus scale out or in for any services within the scale unit? And then there's also policy enforcements, like the geopolitical reasons that you have to do everything within the territory, or the data has to be encrypted at all times, at rest and in transit, etc. And user security access, make sure that people get authorized to access the system as they are authenticated. So that part would address the running of the system, but how is it running? What is the user experience like? How is each region working? How is each country working? So that would mean we also have to have ways to monitor the system. We need to understand when the problem first start brewing, because when you have this many systems running and they fail over for each other, a small glitch isn't going to be very noticeable. The user won't even feel a thing. However, if you don't address that and wait for it to ripple, to get in the ripple effect, by the time you realize there's an issue, by the time the user reports the problem, it's already too late. Your SLA is broken and users are impacted. So we want to find out how the system is running as quickly as possible, and we try to mitigate the incidents as quickly as possible, just to give the user a seamless experience. So over the past couple of years, there has been an increased requirement for control plane-centric projects in our organization. However, due to the complexity of the functionality and the increased adoption of open source software, deployments to multi-tenant support, and deployment to multi-platforms, more than 50% of these engagements are actually withdrawn. Some of it is because Microsoft deemed it infeasible, and some of it is because the client lacks the resources. So my team set out to run some experiment to see if there are ways to speed up the process so that the control plane doesn't become a huge burden in the software development process. And we loosely categorize those 5 functional areas of the control plane to 2 big components. The first part is system management, and the second part is the system monitoring and incident mitigation. Our hope is we want to create a positive cycle where we can easily deploy our applications, get real-time feedback on the resource allocation and application execution, and quickly understand the fault scenarios and mitigate it. And the goal is to create a system that is efficient and also self-healing, so that the user doesn't, the user will just be happy. So the first part is the managed application, and we use that to address the system management part of the functionality. And managed application is an Azure offering that is Azure offering for ISVs to distribute and manage their software offerings on Azure Marketplace. It's very similar to a solution template in that it packages all the infrastructure, the services, and the applications in one software solution. And then you can publish it to either Azure Marketplace in the case of the external client, or to Service Catalog for internal use. Many Azure services use managed application to implement their functionality under the hood. For example, AKS, Azure Kubernetes Service, when you provision AKS in Azure Portal, when the deployment is complete, you're directed to a management page where you would see what the nodes are, what pools are created, what are the networks set up, what workloads are running, how to monitor those, and the overview. So that is, in essence, a control plane for the AKS cluster. Under the hood, Azure actually creates a second resource group, which is a node resource group that contains all the physical parts that runs or that supports the cluster. For example, the virtual machine scale set, the VNets, and all the good stuff that goes with that. So now you can see why it's a natural choice for us, because now we can tap into everything that Azure has to offer. We can use Azure Active Directory for security, role RBAC control, managing identity and policy enforcement. And we can also use Azure Portal for customized management GUI, and use Azure CLI for automation. So for the user, they do not need to learn a complete new tool set. It's a familiar tool set they already work with. It's very easy for them to get adjusted to managing the application this way. And the other part of this is Azure Managed Application supports deployment using either ARM template or any kind of infrastructure as code scripts. And Terraform is Terraform. You can set it up to deploy to Azure. You can set it up to deploy to GCP. It's going to work. Whether it's desirable or not is questionable, but it's doable. Oops. And then the next big component is SLO-based system health modeling. So we are all familiar with dashboards and metrics. And those metrics are like service level indicators that tells us how the system is running or how the service is running. It will show us like CPU, memory, I/O usage, throughput. It'll tell us what's the error rate, the latency. However, when we have a complete software system, it doesn't give us a direct view of whether the system is healthy or not. And I'll give you an example. Imagine I'm looking at a web page where I can search my my company benefits. I put in my search criteria, what's the difference between this year and last year? I click on submit. The response comes back, but the page didn't display properly. Like some of the company logo and the forward and backward buttons are missing. However, all the content is there. I can still find the information I need, and I can navigate the site without any problems. On the back end, if you were looking at the metrics, you may get a service that has an error rate of 100% or a very high percentage, 50% or whatever, which could potentially indicate a problem, which is a problem. But for the user, it doesn't impact them that much. So it doesn't tell you, the individual metrics doesn't tell you the complete story. And I'll give you another example, same use case. I put in my search criteria, I click submit, and it takes forever for the page to load. When the page does eventually load, everything is displayed properly. I have all the nice graphics and everything, and I can navigate through. But every time I click on any link, it takes forever to load. If you were to look at the backend metrics, everything is probably in green and all happy. There's no error reported anywhere. But the user impact on the front end is much worse than the previous example, isn't it? So that is why we would like to adopt this health modeling so that we can use contextualized metrics information to get a conclusion on the system health condition and present that to the user. So the approach we used is SLO-based system health modeling. SLO is a service level objective. It is basically what the user experience is. It's a target that user is looking at. So in that example of the search, after the user input a search criteria and hit submit, their expectation is the results should come back almost instantaneously, because that's how this day and age, that's how it works. Everything comes back really quickly. If I wait like 10 seconds, it's eternal. So we have this top level to say, okay, my request needs to come back within a second or two. I could allow occasional resubmit, but I definitely don't want to submit 5 times just to get one response back. So then we can break it down to see, okay, within the system, when we have to process this search request, what needs to happen? How many calls are happening? Are they sequential? Are they concurrent? How much time is allowed for each portion of the request? And how long does it take for the network transmission? What's the network latency for the request to get to the back end and for the response to reach the front end to the user? So once you have all these target numbers, you can run some load testing to get the system steady state to see if it would meet your top level user SLO. If it doesn't, you can adjust and optimize your code until it actually meets the SLO. So basically, you would have an individual SLO for each component, and then you would aggregate the component health to calculate the system level, the scale unit level health. And once you have the scale unit level health, you're going to aggregate with all other scale units to calculate a region level health. And that is not something that's as cut and dry. Because if you have a region that has 10 scale units running at 30% saturation, losing 1 or 2 scale units may not be a big deal. Your system would still be healthy because the other scale units would be more than capable of carrying over the load. However, when you have a system that has 2 scale units and each is running at 50% saturation rate, losing one could be like a all hands on deck kind of a affair, right? Because your system is on the verge of maxing out. So this health condition is very much contextualized, and it's also very much tailored to your specific system need. So you have to look at your system, the user expectation, and go from top down and then from bottom up to aggregate to get that. And to help with that, Azure has a variety of tools. For example, Azure has Azure Monitor, which automatically collects a lot of metrics and logs. And you could also set up diagnostic settings to export these metrics to Log Analytics Workspace. And once this data is in Log Analytics Workspace, you can use KQL to query and then to aggregate different metrics information to calculate that health condition for the individual components as well as the scale unit level. And then because we have all these dynamically constructed scale units, they come and go, depend on need. We also use Azure Resource Graph to facilitate the resource inquiry part of it. So we don't have to hard code and say, oh, I have 20 scale units running. These are the scale units. We can just run a query to say, what are my scale units running in this region? And give me back all the health condition. So that is our solution. So now I'm going to move on to a quick demo. And before I start the demo, I'll explain to you a little bit about the our test POC system. Because we implement this as experiment, we created a point of a POC system. We have 3 components in this POC scale units. The first one is an event hub that takes incoming user request, and then an Azure function that gets triggered when the event hub request is received. And then a storage unit, a storage account, where the Azure function would aggregate the incoming request and write the responses to. And on top of that, we have a client sample. We have a sample client that simulates random calls to these event hubs to simulate traffic. So now that we understand how the scale unit is working, oh, I forgot to start it, did I? I'm sorry. I'm going to start my scale units. I'm very sorry. Just give me 1 second. Okay, so my test application now started to send requests to my scale units. So you're not going to see anything until in a little bit, but you can see there is actually 18 scale units in process, and they go across 3 different regions. Nothing is coming, so it considers everything is unhealthy. And so at a glance, you're going to get a very direct view, how my system is running. It's going to take a few minutes before the data will pop in. So let me go to a different dashboard. And this is a dashboard created using both auto instrumentation and custom instrumentation using OTel SDKs. It's what we call a scenario-based dashboard, where so we have the incoming request, the total request is this number, and it tells you the system is healthy or not, and it also shows you the dependency for these requests and how each dependency is working. What's the latency for 95% of the request, and what's the availability of the service, and how many requests are coming through to these services. As you can see, the management.azure.com, which is the ARM service from Azure, actually got a little bit of throttled. But other than that, the system is 100% available. So this is done through both auto instrumentation and custom instrumentation. And we can also, once you click on the, if you want to know the detail of how each component is responding, you can always go to a more detailed view where you can get the more service level indicators to see, okay, so how these requests are faring, and if you need to do any troubleshooting, you can certainly use this for a more detailed information. Let's see if the data start to trickle in. Nope, still, well, something is coming through. Yeah, some of the scale units start to pick up. As you can see, as they start to pick up requests, they turn to green because they're actually processing request. So the idea is these requests should come to these scale unit pretty evenly. There shouldn't be any, more or less requests between one from the other. And they should all be processed in a reasonable time. So that was the health condition. Although it looks like the request isn't coming through evenly, because some do have requests and others don't. So this could potentially indicate some issue with the upstream service, where the requests are being distributed. Maybe that algorithm need to be checked out, because it's apparent that some scale units are getting requests while others are not. I'm not sure how long it's going to take for the other information to trickle in. But from this top view, you can see you can gather the health information for each region. It shows you how many scale units are deployed in that region and what the health conditions are. Yeah, we know it's all failing. And you can also, here's another filter where you can tell you, which scale unit is, it's all color coded to show how the health condition of the scale units are. And the top level is your user experience. It tells you what the user experience is seeing, how many requests are coming through, or how long it takes for them to get a response. So that's the idea. So if you are an executive and you come to this view, even without knowing what the system is doing, you'll get a very direct view to see, okay, my system isn't running that great, or, oh, my system is flying. And you can also, filter to only see degraded or unhealthy scale units. And then on the individual scale unit level, if I want to see, what is causing my problems, I can actually see, this is really strange. The data is trickling really slow. Because we are exporting the Azure Monitor data to Log Analytics workspace, there is a bit of delay in that data export process. And here you can see all the service level indicators to help you with a further troubleshoot. And then if you were to look for the managed application or the scale unit level, you can click on the link to go to the scale unit level. And this is that management GUI that I was talking about that you can customize. You can implement custom resource providers to implement your system-specific management tasks and add icons here. Like here, we added a few example ones to restart the Azure function or to drain the traffic that's coming to this scale unit in the case of maintenance, so that these traffic can be redirected to the other scale units. So for any managed application for any managed applications apps, there's two resource groups created. The first one is a managed application resource group, which is what you're seeing now. It contains only a managed resource group. And the managed resource group is where all the actual resources are deployed. So now you have the separation of the resource groups, and you can set up separate access roles to allow access to either. So the developer may get access to the managed resource groups so that they can come in here and get some more detailed view or make adjustments. But the operator may only have access here to handle the operational tasks. Let's see if this is running better, if I have the data over more. Not really. Still, let me go to a different region. Okay, well, it is trickling in. I think, well, why don't we do this? I'm going to show you a quick demo that my coworker did, and on the management tasks, and also demonstrates the RBAC.
We're now going to take a look at some example scripts that an ops or dev team member might write to simplify or automate common tasks from the command line instead of using the portal. This will also allow us to see the managed app RBAC capabilities in action. In front of you is a VS Code editor with the command line, a bash command line in the bottom center. Up here, we see the scripts folder with some example scripts. We can take a look at this restart aggregator. This really is just some basic bash and AZCLI commands. And so if we run the list aggregator, I currently have read-only rights to the subscription, so we can see this return all the resources in a resource group. However, with read-only access, restarting the aggregator actually restarts the function app inside the scale unit, or attempts to, and so you can see that it denies me because of an authorization. I've now been granted the rights to modify the scale unit, so if I run the same command, we can see that after it runs its internal queries, it issues the command to Azure and it executes without error.
Yeah, so that shows you how this works. And let's get back to our scale unit and see if the data aggregation is a little better. And that was Todd Pinland, my coworker that was doing the demo. Excellent demo. So the scale units are getting traffic, but somehow the Azure functions are not being kicked off. Actually, there's scale units that's not getting traffic. So it seems like the system is definitely in trouble because like some scale units are not getting traffic at all. That is a sign of upstream service, that redirect thing. And then my Azure function doesn't seem to be a kickoff. I guess the demo card isn't with me today. Okay, so I was hoping that I could show you, because sometimes when, you may see the incoming request is green, but aggregation duration is red, which means the Azure function is running slower than expected, but the incoming request numbers are fine. So that's a time when we might need to make a decision as to, do we reduce the number of RUs on the event hub so that not as many requests would come through? Or do we increase resource allocation on the Azure function so that it could run faster to handle the load without any problem? So now you can see how this view is going to help us see the bottleneck of the internal system between the dependencies and help us make decisions on making these adjustments. And once the adjustments is made, for example, if I increased the resource allocation on the Azure function, now you might see a different dynamics. You might see the incoming request getting too hot, and Azure function may be more than capable of handling the incoming request. So that would help you to form the cycle to optimize your system and to reach a optimized state where all resource allocations are running efficiently, so you don't waste any, you don't over provision or under provision. And it'll also show you some of the resource, how some of the services, how they respond when they reach, as they get closer to their scaling limits. Like Azure will tell you, okay, this is the limit for, say, Event Hub, but it doesn't really tell you as you get closer to that limit how Event Hub is going to respond. But with this kind of metrics and calculation, you're going to get a very direct view. So that is our demo. And now let's get back to our presentation. And I'm very sorry today. It's I forgot to turn on the demo. So how do we get started? We've seen it in action, and we've heard, the reasoning behind the control plane and how it can be done. So where do I start? I would say there are 5 steps that you can follow. The first one is to define managed application. And here is where you define, the configuration of the scale unit, the dependencies, and how to deploy. And then you can implement any custom resource providers where it's necessary. So your system may have some special needs that is not generic to everyone, that's not being handled by the managed application. So you can actually implement some custom resource providers to help resolve that and customize that management GUI that I just showed you to facilitate the task for the operator. And you also would need to define SLOs as KQL queries. This is actually a pretty major step because you have to look at the system to get those breakdowns and run a lot of tests to get the system response under steady state. And once you have that steady state and you have the aggregation and you can create this KQL query to calculate system health, you'll probably continue to make changes to that as you make adjustments or make improvements over the feedback that this is going to provide you. And you'll need to create global and detailed dashboards. Oh, I forgot to mention Azure Managed Grafana. It is our visualization tool, and that is what we use to create these dashboards. And then the last part is to prepare for incident mitigation. So we have the dashboards and we see the system not healthy. So we can set up alerts on either the dashboards itself or in Azure Monitor to alert people, something is happening. And with each alert, we can set up action. With Azure Monitor, we can set up action groups to address these, either through automation or through manual process. The idea is over time, it's going to give us a history of these incidents and how they're addressed. And then we can use these feedback data to go back to our application to say, okay, it's been failing this way at this condition. Can we address that? So these historic data are very valuable for improving the system stability and efficiency. So now it's our question and answer session. And I posted the link to that POC experiment repo where you can see all the dashboards implementation and all the scale unit definition, etc. And I also put my contact information on screen so that in case you have any questions that you'd like to email me. And the last page is the references to all the Azure services that we used in implementing the solution. So you can just click on the link and learn more about it. That's it. Thank you.
All right. Thank you so much. We appreciate you guys tuning in. And we want to thank our speaker, Yang, for doing a great job today. If you have any feedback, we'd love to hear what you have to say. So you can find the link for our survey on the screen in the chat, which I will put now. And I know Yang had a survey link as well. So let me go ahead and put that up for everyone. And once again, thank you for your time today. And we will see you next time. Have a great day.